Okay, so hello everyone. So to those of you who do not know me, my name is Bahjat. I'm a master's student in the computer science department under the supervision of Professor Michael Elad, Miki. And I am moving to a direct to PhD track. And this is my thesis seminar, basically. We will be talking about the work that we did during the past year about Langevin Dynamics in image restoration. Okay. So our story starts from image denoising, one of the most well-known and well-studied problems in image processing. We start with a noisy image, an image with visible visual noise. We'll try to build an image denoiser, which will output the denoised image, an image that we would want it to be clean and without noise. So this topic has been heavily studied for tens of years, and some people thought of it to be dead, that it's done, that we have achieved everything we can in image denoising. But in this talk, we will talk about some recent discoveries and developments around this topic. We'll start from some brief introduction to the denoising topic. Then we will move on to discuss some more recent work in image synthesis. And then we will finally talk about the work that we've done. Okay, so when I say image denoising, I'm actually more focusing on the removal of additive white Gaussian noise from the image, which basically means that when I take the noisy image and I want to build a denoiser, I assume that the noisy image was built from an original clean image, a good image, that has been added to a Gaussian noise, a noise image that follows the distribution of the Gaussian, the normal distribution, with a standard deviation sigma 0. Now, this is far from a trivial task, because basically our goal is to remove as much noise as possible from the noisy image while preserving the details that were originally in the image. Basically, we're talking about an ill-posed separation task. We get the noisy image, and when we want to separate it to its original image, as well as the noise. Now, traditionally, how were denoisers built? How were denoisers designed? We had some idea of what an image should look like, some properties that the image should have, and we used this information, this model of an image, in order to build a noise filter. Some examples are, some prominent examples are sparse representations and Gaussian mixture models, stuff like that. That was how denoisers were designed. But in the last decade or so, recently, the state-of-the-art denoising is dominated by deep learning, by supervised training of neural networks. So we just take a lot of data, we train a neural network, and that's how we get a denoiser. This has been the state-of-the-art for about a decade. And when I say training or learning, basically what do denoisers learn? When I take this neural network that I call a denoiser, and I teach it to denoise. So obviously they learn to denoise, right? They learn to separate noise from image content. So because of that, we think that this denoiser, although we did not explicitly tell it a model about what image content should look like, it does implicitly contain some information about the image distribution, about what an image should actually look like. So can we leverage this information for other tasks? The information that is embedded in a denoiser, can we use it to solve other tasks pertaining to the same image distribution? The answer is a resounding yes. Here we will show a few papers that did this. These are, of course, some of many papers that did this. For example, in 2013, the plug and play priors paper used the denoiser in an iterative scheme in order to solve some inverse problems. In 2017, the red paper from our group, from Mickey's group, used the denoiser in a regularization scheme, also for solving inverse problems. As you can see, these are highly influential papers. In 2019, Song and Hermon from Stanford came up with a way for using a denoiser for generative modeling, for generating images out of thin air. They improved upon this again in 2020. And 2020, Simoncelli from NYU also introduced a way to solve inverse problems, subset of inverse problems, using the same ideas presented in this paper. So right now we will move on to focus on this paper because we rely on it in our work, and discuss their core idea. So we will talk a little bit about image synthesis or image generation, which is basically synthesizing images out of thin air. I want to tell my computer, give me a picture of a person. So this has been basically dominated by a tool called GAN, Generative Adversarial Networks. And as you can see here, for example, all these images are not real. They are generated. Someone just clicked on a computer and this photo of a dog or this bubble was formed. All these people are not real. They are generated by a GAN called StyleGAN. And as you can see, they look very real, but they actually aren't. There are not pictures of people. So why do we do this? Why do we synthesize images? Well, first of all, it is fascinating that the computer is able to do this. It also is a testament to the fact that we have seized the image distribution, that we know what the distribution of face images look like or dog images, and it could be used also for other needs. Now, the question here is, could we synthesize images differently? Can we synthesize images without GANs? So this paper says yes. They devised a way to synthesize images using only a pre-trained image denoiser, using the information in that denoiser. The core idea is something like this. So what do we mean when we say, let's generate an image? This is the same as saying, let's sample from the distribution of images, P of X. If X is a real image, P of X is their distribution, and I want to sample from this distribution. So their algorithm works like this. They initialize with a random image, random noise image, x0, and they follow in an iterative equation, they follow the direction of the gradient of the log of the probability. So let's see what's happening here. Let's assume that we don't have the log, we follow the gradient of the probability. That is a gradient ascent algorithm, right? We follow to a more probable image, an image with a higher probability. Now, if we optimize the log, we also optimize the probability itself because the log is a monotonic function. So if I follow the direction of the gradient log probability, I am increasing the probability of my image. That's how we climb to a more probable image. And in an iterative equation, we reach an image that is highly probable, which we then say that it is sampled from distribution of images. Now, if this iterative equation was done just like that, then it would probably collapse to some kind of local maxima. So in the algorithm that is called Langevin Dynamics, they add some randomness to the steps. They add this vector zk, which is a standard normal vector, in order to add stochasticity and to say that this iterative equation, basically, it converges to a sample from P of X. Every time it converges to a different sample. Now, this gradient of the log of the probability has a name. It is known as the score function. And when P is unknown and without any assumptions, it is generally intractable. Why do I say this? For example, we start with a random noise image, right? So the probability of the noise image being real should be 0 in the general case. And log of 0 is not even defined. So that's why the score function is intractable, among other reasons. Now, there have been some ways called score matching that try to approximate this, but their image generation performance does not compare at all to that of GANs. So we will not be focusing on those. We'll be focusing on this paper by Song and Hermon. So just a word about Langevin Dynamics. This iterative equation, if P of X is well defined, the log of it is well defined everywhere, and under some other mild conditions, Langevin Dynamics guarantees that this iterative equation will converge to a sample from P of X. Now, as we said, there are problems with this score function, that it is intractable in the general case. So what someone in Ramon did is that they replaced the P of X with a blurred version of it, P sigma of X. What do you mean by blurred? Instead of looking at the probability of X being a real image, we look at the probability of X being a real image with some noise, with some Gaussian noise with a standard deviation sigma. This, for example, helps us in the well-definedness because the Gaussian noise distribution has infinite tails, right? So it is not exactly zero anywhere. So the log is well-defined, for example. Now, while the original score function was intractable, the blurred score function, the gradient log of P sigma, is actually exactly equal to d of x minus x itself divided by sigma squared. What is d? D is the minimum MSE denoiser. It is the denoiser that minimizes the MSE loss, the mean square error. Now, of course, this d is kind of theoretical. We don't really have it. It is an NP complete problem, but do have some great approximations of it. As we said, the deep learning has led to unprecedented levels of performance in denoising. So the current state-of-the-art denoisers are very good approximations of this optimal denoiser. So what Sangha and Armand did is that they present the annealed Langevin Dynamics algorithm. They use this P sigma instead of P. They start with very high sigma in order to capture the distribution everywhere in the pixel space, and they gradually anneal it down to near zero. With every step, we decrease this sigma until it reaches very negligible levels, so that the sample from P sigma of X looks very much like a sample from P of X, the non-blurred version. Why? Because the noise is very negligible. It is not seen to the naked eye. So they set the step size to be proportionate to sigma squared, and they go on with this iterative algorithm, that is P sigma and not P. And they gradually decrease the sigma until they reach near zero levels, as we said. And that's how they obtain a sample from P of X. That's how they generate an image out of thin air. I remind you that the gradient log here, the blurred score function, is approximated using a denoiser. So the algorithm looks something like this. We start with random noise. We do some operations, as we see here, and we apply denoiser with a high sigma, very high sigma, sigma 1. Then again, with a slightly smaller sigma, and so on and so forth, until we reach a very small sigma. And that's how we obtain our X hat. That's how we obtain our generated image. So I just want to emphasize that I'm not talking about some niche algorithm that some paper did. We're talking about an algorithm that its subsequent papers have achieved state-of-the-art performance in image synthesis on very well-known datasets such as CIFAR10 and ImageNet. Here we show some of the results. There are some generated images, face images, bedroom images, tower images. This is from their paper from 2020. 2021, they even improved upon this. These are high resolution face images that are all generated. Here you can see results on CIFAR and MNIST, as well as some face images from Celebay. And here's, for example, some samples from the state-of-the-art, the current state-of-the-art on ImageNet image generation. This is also something that follows the algorithm that we've seen. And look at how real the images look. So we're talking about the state-of-the-art image generation algorithm. Okay, so now we will move on to discuss our work. So we've discussed image denoising. We've seen that it's great. It can denoise images very well. We've even seen that denoisers can be utilized for synthesizing images in state-of-the-art level. So is denoising dead? Are there any drawbacks yet to be addressed in image denoising? Is there anything left for us to do? So let's see. Let's look at this photo of the Tourifel. And this is a noisy version of it. Now I take this noisy version and I apply a state-of-the-art denoiser on it, an MMC denoiser. I get this image. Now, the denoiser did a pretty good job. It removed almost all the noise. But look, for example, at the clouds. Look at the small architectural details that make the Tour Eiffel so great. They appear a little blurry, right? So we wanted to fix that. Let's see where that comes from. So the deep learning-based denoisers train their denoiser in order to minimize the expected reconstruction. They minimize the MSE, the expectation of the difference between the reconstruction x hat and the original x. Now it can be shown using some algebra that the optimal minimizer for this is when the x hat is equal to the expectation of x given y. Y is the noisy image, x is the real image. So I look at the expectation of x given y, that will give me the best reconstruction. This is the optimal minimizer. Now, of course, this is a very, this approach has its merits, but the problem is that it inherently leads to blurry results, especially when we're talking about moderate and high noise levels. So while let's see an illustration. Let's assume that this is the image manifold, a one-dimensional line in a two-dimensional space that is the manifold of real images. Let's assume I get a noisy image that is this red dot. And all these images could have explained this noisy image. All these images could have been the original. So when I talk about the optimal minimizer, the MMSC, it will be their expectation or their average, which will sit somewhere here in the middle, right? Because it's the average of all these points. Now, this result, as you can see, sits outside the image manifold, which means it will not look like a real image. For example, in the example we've seen before, it was blurry. So it does not exactly look real. It is an average of some real images. What I want, if we want to improve the visual quality of this denoised result, we would actually want one of these images, one of the real images that could explain the noise image while still being on the image manifold. Now, what I've just said has a very well-defined definition. We want to sample from the posterior. We want to sample from the probability of x given y from the distribution of real images given the noisy image. So in our case, we want to take not exactly the real images with some small noise sigma. So how can we sample from this distribution? We will use Elad Langevin Dynamics that we've seen in the prior work. Now let's remind ourselves about Elad Langevin Dynamics. We sampled from P sigma of x using its score function. Using this iterative scheme, we climbed a more probable image and add some noise. Now, if we want to sample from the conditional distribution from P of x given y, we just add the given y here to the score function. That's how we obtain the conditional score function. But we still don't know how to get it, right? We want this algorithm. We know that it will give us a sample from the posterior distribution, but we still need to derive this conditional score function, the gradient log of P of x given y. So we use the base rule for this. The base rule will help us write y given x and not x given y. And it will add this gradient log of P of x. Now this is the original, this is the blurred score function that can be approximated using a denoiser. We can get a very good approximation for it. Let's look at the second term. What we see here is we have y and x, and more specifically xk. Y is the measurement that we have. It has a measurement noise with sigma 0, a known noise variance. But xk is a noise version of x that is synthetic. In our we did not get this as input. In our Langevin iterations, we assume that xk is a noise version of x with noise sigma k. Now, because it is synthetic, it is under our control. We can decide what the noise level is. We can make some assumptions on it. So what we'll do, instead of starting from a very high sigma as in the synthesis algorithm, we start from the sigma that we have, sigma 0, and gradually go down to near 0 levels. We'll take slightly less noisy versions, and that's how we will denoise. The idea is basically that we want to recover a sequence of gradually less noisy images. We take the y, the noisy image with the high noise, and we gradually peel more and more layers from it until we get some negligible noise. So if our final output is XL, which is the real image X with some small noise, the one step before it would have XL minus 1, which is the same, plus an additional uncorrelated layer of noise, an additional independent layer of noise, and so on and so forth. Right? We add more and more layers of noise, which we go backwards in time till we reach X1, the one we started with, which we assume to be Y, just Y without the additional layer of noise. Now, if we look at the difference between Y, for example, and this blue X or any other XK, we see that the difference is just these noise levels, just these noise layers. So the difference between Y and a given XK, any step of the algorithm, will be just a noise vector. It will be independent of the XK itself because it's just the additional layers of noise. And its variance will be equal to the difference in variances between the noise in Y and the noise in XK, which is sigma 0 squared minus sigma k squared. So if we look at the term that we were trying to derive, we were trying to derive the gradient log of P of Y given XK. XK here is a known quantity, so we can subtract it. And we get this difference, which we just said is independent of XK. So we can remove this dependence of XK, it does not matter. And we get gradient log of this probability distribution, which is a very known distribution. It's the Gaussian distribution with this variance. So we just substituted with the known Gaussian PDF, and we get this term. If we do a log and a gradient, we get this term, which is from known quantities, from Y and XK. We can calculate it analytically. So if we plug this back into the conditional score function using the base rule, we get that the conditional score function is this original blurred score function plus this analytical term. And I remind you that this term can be approximated using a denoiser. So
can I ask you a question?
Please leave the questions till then. We will have a dedicated
sorry.
session. Thank you. So we'll use a neural network that approximates the blurred score function, which is basically the denoiser. And we obtain this denoising algorithm. We will iterate over the sigmas from 1 to L. And in every sigma, we'll do a few iterations where we follow this Langevin update formula with the gradient, which is the approximation of the original score function and the analytical term that we derived. I remind you that this is basically a denoiser residual. So, okay, does this work? Let's see. So here we start from a noisy image. In this example, the sigma is 150, where the pixel values are from 0 to 255. And here we see the intermediate steps of our algorithm. We gradually obtain less and less noise images until we get an image with negligible noise. As you can see, we have denoised it very well. Let's look here, for example, at the example on the left. We're talking about 64 by 64 image of a face. And here are noisy versions with different noise levels. And here we can see an output of an MMC trained denoiser. You can see that as the noise increases, the picture of the face looks more and more blurry. Look at the hairstyle, for example. It gets much more uncertain. But in our algorithm, we have obtained the same level of high perceptual quality across all noise levels. In the bedroom example with the bigger image, you can see it as well. If we zoom in, look, for example, at the wood here, in the MMC approximation, we get a blurry panel, while in our algorithm, we can clearly see the texture on the wood, which means that we have a much higher quality image. For example, here in 256 by 256 images with noise 100, look at the difference here. You can see in the hair area that it is blurry, and here there is a very high quality image. So we also mentioned that our algorithm is stochastic, right? It has some noise elements and such. So does that mean that for the same input, it will produce multiple outputs? So yes, let's look at these noisy images. And what we see below is just different samples from our algorithm. For example, here you can see that this woman has different hairstyle, different color of eyeshadow, different face expressions, different face details. The general structure of the image is preserved across the different samples. You can see that the small fine details differ. If you look, for example, at his hair or eyebrows, you can see that they differ, but it's still the same general structure of the image, because we still want to be a valid denoising result to this noisy image. So we have produced multiple samples, but are they valid? How can I be sure that these are valid denoising results? So what we did, we looked at the difference between our denoise result and the noisy input. And this difference should be the noise, right? It should be the residual noise. It is also called in the literature as method noise. So we examined our method noise and performed some tests. In order to test that it is uncorrelated, we tested the Pearson correlation coefficient among adjacent pixels. Pixels that are next to each other, we made sure that they are not correlated. We tested the normality. We performed a statistical test from Pearson and D'Agostino that tests whether the current vector is considered to be Gaussian or not. And we tested the standard deviation. We looked at the empirical standard deviation of our vector, and we compared that to that of the actual noise. For example, if the noise was 100, then the standard deviation of this vector should be 100. And the results were very positive. We got that the Pearson correlation coefficient is almost 0. The p-values of the statistical test were great, and the standard deviation matches the actual noise standard deviation perfectly. We also looked, for example, at the difference between two samples from the same input from our algorithm. And you can see that as we increase the noise variance, the difference between the samples also increases. You can see that the colors get brighter and brighter. Okay, so we've seen high perceptual quality denoising results. We've seen that they are really valid denoising results. Now, it is still interesting to see how they perform in terms of MSE. So there is a theory from a paper by Blau and Michaeli from Technion that talks about the perception distortion trade-off, that there is a trade-off between high perceptual quality images and distortion measures such as the MSE. That if we want higher perceptual quality images, we have to sacrifice in terms of MSE performance or PSNR performance. They proved that the sacrifice in MSE should be no more than a factor of 2. And if we look at our results, we took 64 images, looked at the denoising results from an MMC denoiser, the same one that we used in order to approximate the score function in our algorithm, and our results. And we looked at the ratio between the MSE that they achieved and the MSE that our algorithm achieved. And it is much in line with the perception distortion trade-off theory, that it is almost 2. Okay, so that was our discussion regarding denoising. And we wanted to expand this beyond that. We saw that we achieved high perceptual quality results in the denoising problem. We wanted to apply that to a different problem. So we looked at the problem of image in painting, which is when we observe an image that also has some noise, but also has some missing areas. And we want to recover the original image. Now, this is a more difficult problem than denoising, but we wanted to tackle it similarly. We wanted to use Langevin Dynamics in order to solve the noisy image in painting problem. So there are a few problems with that. We can't apply the same exact algorithm again here, because in our stochastic denoising algorithm, we initialized using the input, right, the noisy input y, and we got gradual less noisy images. In this case, we can't, because y has missing areas. I can't initialize with this empty square. So what we did, we went back to what they did in synthesis, and we initialized using a random noise image. Started from a very high sigma, then gradually went down towards sigma 0, the noise in y, And then we got gradually less noisy images. There's also another problem that here, this is a different problem than denoising. So the derivations we made regarding the score function are not the same. So we had to derive this again. I will not show the entire derivation because of the time limit in this lecture, but let's look at the final results. So what we did, we split the derivation into cases. M, which is the observed images, the mask, the observed pixels, sorry, the mask of the in painting, which are the pixels that are not removed, and R are the remaining pixels that are removed. So in the case where sigma is smaller than sigma 0, which is the second part of the algorithm, after we obtain something that is similar to the image with noise sigma 0, but with the filled area. If we look at the visible pixels, this score function is exactly equal to the score function in the denoising scheme. We have the original blurred score function that is approximate using a denoiser and the same analytical term that we have. And in the case of the missing pixels, well, we don't have any information to rely on. So we had to rely on only the prior information provided by the denoiser. Same goes for when the sigma is higher than the sigma in the input. We also don't know anything about the missing pixels, so we had to only rely on the prior information from the denoiser. And as for the known pixels, well, right now we are in this area. We have a sigma that is larger than the input. So that means that I know a less noisy version of this pixel. So I need to move towards it. I move towards Y, away from the current X. That's how we get our gradient. So we just use this new score function for in painting, initialize with random image and go through all these sigmas. That's how we got our in painting algorithm using Langevin Dynamics. Here's an example. These are the original images. We observe a noisy version of it and without the mouth area. You can see that when we give multiple samples from our algorithm, for example, here in the mouth area, we don't know what was here, right? The image was removed. So sometimes the mouth would be closed, sometimes it would be open. Don't know what color lipstick this woman had. As you can see, there is much higher variance in the results. We can also look at these images. This is a much more practical problem of removing text overlay from over an image. If we have these images and text over them, we can remove them using in-painting. We want to in-paint in the missing areas of the text. As you can see, we get very good reconstructions. So up until now, we discussed image denoising and image in-painting. Solve these two problems, obtaining high perceptual quality results with multiple samples with a stochastic algorithm that needs sample from the posterior. But we did not stop there. Wanted more. We wanted to solve more general problems, not just denoising and in-painting. So we thought about generalizing to a more broad family of problems. So we looked at linear inverse problems, which are the recovery of images from corrupted measurements. This family includes denoising, the problem of deblurring, where we have blurry image and we want to remove the blur, in-painting that we discussed, demosaicing, tomography, it could be used, and the image super resolution, where we have small image and we want to increase its size, and many, many more problems. All of these problems fall under the umbrella term of linear inverse problem, where we assume that we observe a degraded version Y, which is formed by taking the original clean image X, multiplying it by a linear operator H, applying the linear operator on it, which can be assumed to be a matrix, and adding some Gaussian noise of a known standard deviation, Z. Okay, so we are given Y and we want to recover X. Well, we can do this using the same way we solve denoising and in-painting. We can use Langevin Dynamics. So we want to derive the score function, we use the base theorem as before, and we want to calculate this likelihood term of Y given Xi. So let's try to do this. We have Y given Xi. Xi is a known quantity, just as we did in denoising, but this time I want to subtract H Xi, which is also a known quantity, because xi and y are not of the same size, so we can't really do y minus xi. And now we substitute what we know about y. Y is hx plus z, and xi is just x and plus a noise element, ni. So I substitute xi with x and ni. I get this term. Hx and hx can go away. And I just have z minus h and I. Now, this vector is interesting because z is noise in the measurement. It's the noise in y, right? It is Gaussian. Ni is the synthetic noise, right? And multiplying Gaussian noise by linear operator remains Gaussian. So if I assume z and ni to be independent, then what I have here is a Gaussian vector. That's very nice. A Gaussian vector, I know its properties, I know its probability density function, I can derive its score function. But the only problem here is that z minus h and I is kind of dependent on xi. It's dependent in a very non-trivial way because xi contains ni. So I can't remove this dependence. I can't really use this. So it is unclear how to continue from here. So the generalization to general inverse problems from in painting and denoising is not trivial at all. We can't do it the same way. So we did present a solution. We looked at the singular value decomposition, the SVD, of the degradation operator H, which is U sigma V transpose, where U and V are orthonormal matrices, and sigma contains the singular values in its main diagonal and zeros everywhere else. So this helped us in decoupling the measurements. What do I mean? If we look at U transpose Y, and we replace Y with what we know Y is, it's Hx to Z. Look at H, replace it with its SVD decomposition, get U sigma V transpose. If we open the parentheses, get this term. Notice that because U is an orthonormal matrix, U transpose U can be removed. It is the identity matrix. And we wanted a relation with the xi and not x. So replace x with just xi minus the noise in it, right? It's the same. We open the parentheses and we remind ourselves that we started from U transpose y. So what we see here is a relation between U transpose y and V transpose xi. They are related only using a diagonal matrix. So the measurements are decoupled. They are not dependent on each other, right? Because this is diagonal matrix, the first entry in y will depend on the first entry on xi and not a combination of, which helps us in deriving the Langevin algorithm. And the addition here is just a difference between noises, right? Z and ni. We'll come back to this later. But we talked about a relation between U transpose y and V transpose xi. So why is this relevant to us? We wanted to sample from the posterior distribution. We wanted to sample from P of xi given y. Now, because U transpose is an orthonormal matrix, it does not change the information of y. So given y or given U transpose y, it's the same thing. Same goes for V transpose. It's an orthonormal matrix. So it will not change the statistics of xi. Because of this equivalence, we can apply the Langevin Dynamics algorithm on U transpose y and V transpose xi. In the end, we'll get a sample from this distribution, which is V transpose xi. And I can just multiply it by V and obtain my sample from P of x of given y, because it is the same distribution. And just multiply it by V and get my result. That's how I can sample from the posterior. Now, we want to apply the conditional Langevin dynamics on these transformed versions, right? V transpose xi, which I will call x transformed, U transpose y, which I will call y transformed. And if I have the score function of these using this relation here, where the difference between the transformed y and the transformed xi multiplied by sigma will be just this noise element. I need to derive the score function. If I can do that, I can sample from the posterior distribution of any linear inverse problems, which is very fascinating. Now, the derivation is also very complicated here. It involves many different cases regarding the different singular values, because while sigma is diagonal, it still has some different scale in every row. So we had to alter stat. We had to define the noise in such a way that this difference is actually Gaussian and we can derive it. We will not go into the details. We also did a mild approximation. And we ended up with this score function. Now, this is a huge, I know that this is a huge expression. We are not going to explain everything in it, but we will notice that here we have the difference between the transformed y and sigma multiplied by the transformed x. This will be a Gaussian vector, and this will be its element-wise variance. The entire calculations are in the paper, so for those of you who are interested in how these expressions were formed, you can check out the paper. But this is the variance of this Gaussian vector. Notice that it is element-wise, it is diagonal. So, and we've sort of inverted it. Here we can identify the original score function, which can be approximated using noisy residual. And we did not use all of it. We put zeros for the case where the singular value was greater than the ratio of sigmas. It's not important for now, the details of this. But this is a very big expression that is formed using familiar expressions such as the noisy residual and this Gaussian vector and its variance. Okay, so after all this work that we did in order to reach this expression, I want to check out if it works well. And unfortunately, it didn't work well on every problem. So there was still some drawbacks to this. We wanted to solve them. So we remind ourselves that in the new Langevin Dynamics algorithm, the step size was chosen to be proportionate to the variance in the synthetic noisy version in Xi. Now, this step size was chosen for image synthesis. Maybe it does not apply in our case. So after further investigation, we found out that this step size is equivalent to a diagonal approximation of the negative inverse Hessian of the score function, the second derivative of the log P of x. Now, this reminds us of Newton's method in optimization. We follow the direction of the negative inverse Hessian multiplied by the gradient. So we wanted to do the same. So we took our conditional version of the score function and we derived its Hessian, calculated the negative inverse Hessian, and got the step size. Now, in our case, the step size was dependent on the respective singular value of every entry, right? Because we have a vector and it is multiplied by sigma, the matrix with the singular values. So for every different singular value, for 3 cases of the singular values, we got different step sizes. This is not important. The details can be seen in the paper, the derivation. But after applying these step sizes, instead of the original synthesis step size, we got the SNPs algorithm. We solve noisy inverse problems stochastically. This is the same algorithm as before, just with this different step size across different entries and the new gradient vector, the new score function. And we went ahead and tried to solve some problems using this algorithm for solving general inverse problems. So in order to demonstrate, we took the problem of super resolution. The degradation is downscaling by 2 in each dimension in width and height. And we added an additive noise of sigma 25 to the small version, to the low-res version. So here we can see the original image, the degraded one, the low resolution, and our reconstruction. See that it's very high quality. We managed to remove the noise and super resolute it, increase its size. You can see additional examples. You can see very good reconstructions, as well as here, here, and here. You can see that, for example, here in the low-res version, it is not entirely clear that his mouth was originally closed. So in this sample specifically, it was open. And we can also produce multiple samples. So for a given degraded image, for a given low-res image, we can produce multiple versions, right? Because of the uncertainty in the posterior distribution. So if we look at the first row, you can look at the different face expressions, the different eyebrows, right? Different hairstyles. And if we average all these samples from our algorithm, get this mean, which as you can see is blurry because it is an approximation of the expectation of the MMSE. So if we see a broader image, you can see that here we produce 8 samples from every image. We obtain their mean and their standard deviation. You can see that the general structure is preserved, but the differences between the different samples are in the fine details. You can see that they are around the eyes, the hair, the mouth, right? The fine details that get lost when we downscale the image and add some noise, they produce some standard deviation here, some variance. For example, here you can see the background is very black. It is does not have any variance. Okay. We also did super resolution by 4 in every dimension. As you can see here, the uncertainty gets much higher. For example, if you look at the degraded image, not much is clear, but we still produce different samples. As you can see, for example, here, we are not sure if this guy is wearing any glasses or not. So in one sample, he is wearing some glasses, in others, they aren't. Here we have very varied images, right? And if we look at the bigger picture, you can see that in the standard deviation, the colors are much more glowing. There is much more variance in the correct areas, right? So we, of course, are not, we did not just do face images. There are also bedroom images, samples, different samples. And we did not just do super resolution, we also did deblurring. In this case, we used a uniform blur of a kernel size 5 and some noise. As you can see here, for example, look at this kid's different hairstyles, different expressions, right? We have a variance in the output. We also see the mean and standard deviation. And we wanted to see also a third different problem. So we looked at also not just super resolution and deblurring, we looked at compressive sensing, where we take an image, we compress it using a random compression matrix, a random matrix that decreases the size, in this case by 12.5%. And we added noise to this measurement. And from this degradation, we just have an 1/8 of the original image. You see that we have some very good reconstructions that are very varied. Because of the high compression rate, we did not get a perfect reconstruction, but we still got most of the details correctly. We still have some high variance, of course. And as we can see here, if we increase the compression ratio, or basically decrease, if we just compress more and more, you can see that while the uncertainty rises, right? We have a very much higher standard deviation, as is clearly seen here. The mean of the samples gets to look like less and less like a real image, right? Look at the mean here. It's very unclear, it's very blurry compared to the original 25% compression. But in any case, the sample from our algorithm, this is just one sample, right? The sample from our algorithm still has high perceptual quality across all compression ratios, across all levels, because this is sampling from the posterior. So it will still have its high resolution, its high quality, but it does look less and less like the original image because we have less data, right? We had 25% of data and now we have 6%, but still it is high quality. So we've seen that our algorithm, SNPs, performs well on various inverse problems and several data sets. We have high perceptual quality images. So are there any drawbacks to our algorithm? Of course, there are. We have to discuss them. So in order to solve general inverse problems, we had to calculate the SVD decomposition. Now, sure, we calculated only once at the beginning of the algorithm, but the problem with SVD is its memory consumption, not the time. And this hinders our algorithm scalability. In order to work with higher resolution images, we need to calculate the SVD in a much higher dimension. And this is a problem because we need a lot of memory. We also we did see very different classes like face images and bedrooms and towers, but still for each different data set, we used a different denoiser that was trained on similar images. So we worked with specific classes and not just general content images. Now, of course, this is not related to our algorithm, but rather related to the properties of the denoiser used in the algorithm. if the denoiser was trained on face images, our algorithm can only handle face images, right? So we have some ongoing projects regarding this in order to address this problem. This will be hopefully one of the subjects in my future PhD studies. And another major drawback is that SNPs is slow. For example, it takes 2 minutes to produce 8 face images of size 64 by 64. So this is, of course, not a characteristic of specifically our algorithm, but a characteristic of all Langevin Dynamics algorithms. We need more than 1,000 iterations for the algorithm to converge. And this is why it takes 2 minutes. There are some recent works from around the world that attempted to address this. They reduced this 2-minute numbers significantly. And we are also working on something in this regard, hopefully in my PhD studies. And we believe that the technology and the research will address all these drawbacks in the future. So to summarize, we've seen the annealed Langevin Dynamics algorithm, and we used it, first of all, to enhance the denoiser's perceptual quality without pre-training it. Notice that across all this lecture, we did not train anything. We used a pre-trained image denoiser and used it for all these tasks, starting with denoising and high perceptual quality denoising. Then we adapted it and applied it on image in painting. Then we further generalized it for general inverse problems. And we call our algorithm SNPs. This basically shows the huge power contained in the denoiser. The denoiser can solve all these problems while it was trained only to remove Gaussian noise from an image. This is a very great finding. And we demonstrated our algorithm on different problems, super resolution, deep learning, and compressive sensing, all showing high quality results. And we verified all the results using the 3 statistical tests that we've seen. We use this not only on denoising, but we also applied it on the different inverse problems. And that's it. This work was done by a collaboration of myself and Gregory Waxman, Grisha from our group, and under the supervision of Miki. We have 2 papers, the first of which is scheduled to appear in an ICTV workshop in October, and the second one is available on arXiv. So thank you very much for listening. If you have any questions, now is the time.
Wonderful, thank you very much. Questions? Doro, you wanted to ask something?
No, I think I figured it out by myself. Thank you.
Any other question?
I have a question, Bahjat. I'm sorry, I don't have a camera on this computer. Can you go back to the denoising part, the first part? I think yes. Slide 19 or something like that.
Yes. This part?
Yeah. So here you want to sample from P of X given Y. Yeah. You use Bayes' rule and you get P of Y given X. But this is P of Y, the real P of Y given X, right? When you only evaluated it at XK, right? You don't need P of Y given XK. You need P of Y given X evaluated at XK. So you don't need all these sigmas as far as I understand. It's the original sigma of the noise.
Yeah, so we actually did assume that the XK has this sigma K. This is not the original Y given the clean X. This is Y given the noisy X. Because
why not?
We followed the same thing that was applied in Song and Ramon's paper. We used the blurred score function that we talk about the XK in Song's algorithm. They also use the sigmas because, for example, at the kth step, we just assume the blurred score function, the blurred distribution, basically, with the current sigma K. This helps us because when you look at the very high sigma, it captures a much higher volume in the pixel space. So it can give a much more accurate gradients for example, when we initialize with a random image, it helps us a lot.
I see. So K, you have two things that change here as a function of the iteration, right? The noise, the artificial noise that you add, right? And the iterations of the Langevin dynamics, right? So K is the iterations of the outer iterations of the artificial noise?
Exactly, yes. The outer iterations, which change the xk and the sigma k.
Okay, I see. Thanks.
Other questions? Okay, thank you very much, everybody. Thank you. And Bahjat, excellent talk.
Thank you.
Thank you, Bahjat.